Okay, let me start. I'm Tobias Herzke, and this is Frasher Loshaj. We both work at Herzke, and we are presenting today about the Open Master Hearing Aid, a signal for software for signal processing for hearing aid research. In hearing aid research, we develop new algorithms and need to test them with the target group, the target audience, which are hard of hearing people. And to do this, we need a platform, and the Open Master Hearing Aid is one such platform that we will present today. This slide is titled Structure of this openMHA presentation. The title is up there. But, this presentation will take place in 3 parts. I will present the first part, introduction into the problem domain, what means hearing impairment, what is hearing impairment, and how do hearing aids help. The second part is about the openMHA software, what's its purpose, and how does it achieve what it achieves. And the third part is a demo of the openMHA software. We will also have a short demo in the first part about what is hearing impairment. Okay, here you see a picture of the anatomy of the ear. Sound arrives from outside, it passes the pinna, goes into the ear canal, and then the sound in the ear canal excites the eardrum. The sound is then transmitted through these ossicles to the inner ear. The inner ear is filled with liquid, and the sound here is airborne, and the ossicles, they provide some adaptation to the impedance. The spiral here, the inner ear, the cochlea is formed as a spiral, and you actually have 3 compartments, 3 liquid-filled compartments that run along the length of this spiral, and they are separated by membranes. And when this inner ear is excited with the sound, then these membranes also get excited and oscillate. And it happens that there are different resonance frequencies, so to say, at different places in the spiral for different frequencies. So the outermost outermost are the highest frequencies, and the lowest frequencies we have at the apex. So the oscillation of this one membrane. On one of these membranes sits the organ of Corti, which is where basically the sound vibrations are translated to nerve impulses. And I will show you that in the next slide. But first, there are 2 different types of hearing loss. The first is conduction loss that can happen in the outer or in the middle ear. For example, if parts are missing, like the eardrum is missing or the ossicles are missing, parts have been ossified, the path is obstructed, or something has grown shut. So then you have a conduction loss. But far more frequent is the so-called sensory neural hearing loss in the inner ear, which means damages to hair cells here in the inner ear. More than 2/3 of the population will develop sensory neural hearing loss at some part of their life. Hearing loss is generally related with age. And this is what happens in the inner ear. So here's a picture of the hair cells on the basilar membrane. This is a picture of it's also called the organ of Corti. What you see here, these white things, these are bundles of hair cells, approximately 20 hair cells per bundle. And these white things are the hairs that extend in the direction of the camera. We have 3 rows of outer hair cells here above, and 1 row of inner hair cells the inner hair cells actually activate the neurons, and the outer hair cells amplify sounds. They do this by coupling energy into the system that already oscillates. When you want to diagnose if someone has a hearing loss, you usually do audiometry. Audiometry means you play that person soft sinusoid sounds and ask them at what level they actually hear something. And you determine what is normal by getting an ensemble of people who will probably hear normally and then measure their hearing thresholds. And the mean of these hearing thresholds per frequency are then named 0 dB HL, hearing level. So normal hearing by definition means 0 dB hearing level at all frequencies. But there's some variation because it's also only a mean. Yes. Well, audiometry is used to diagnose this hearing loss. And an audiogram shows the extent of the hearing loss. An audiogram is such a diagram where you have a frequency axis from left to right. Usually it's measured up to 8 kilohertz. And you then enter the hearing thresholds into this diagram. The level axis here grows to higher levels when you go downwards. So this picture here then shows a person who has normal hearing thresholds at low frequencies, up to 1 kilohertz, and then a sloping high-frequency hearing loss at high frequencies. The red points are the uncomfortable level. You can also measure, well, draw or turn the sinusoid so loud and ask the person, okay, raise your hand when it's uncomfortably loud. And interestingly, for normal hearing people and for hard of hearing people, often uncomfortably loud is in the same range, in the same region. So when you get a hearing loss, you don't necessarily have excited or elevated uncomfortable levels. Now I want to try to show you a demo. What does hearing loss actually sound like? And we can do a demo by doing signal processing and simulate in signal processing the effects on level and on spectral selectivity of the loss of outer and inner hair cells. So I will switch to this other computer. Okay, I hope you see enough. You see another audiogram diagram, and here on the right are 2 spectrogram displays that are currently empty. Basically, this application is a media player, and I can play sound files from the hard disk and then simulate hearing loss or also hearing aids. And this is bad because the lower spectrogram is hardly visible, so let me make this smaller. Okay, like this. So you see here currently the audiogram of a normal hearing person. I will now switch to the audiogram of hard of hearing person. This is again a high frequency hearing loss. And currently the simulation is not activated. That's why the upper spectrogram and the lower spectrogram are basically identical. so you can hear what's playing. At least I thought you could. Okay. If you have another demo effect. Ah, yes. This is what it sounds like with hearing loss activated, and I can now deactivate it again. And activate. And deactivate. So if someone has a hearing loss like this, he needs a hearing aid, and I can now activate a hearing aid. The hearing aid simulation will be simulated first, and the resulting sound will be fed to the hearing loss simulation. So this is with hearing aid simulation on. Off again. On. And a comparison unprocessed. So you can hear a serious quality degradation if you have a hearing aid and a hearing loss. This is not a shortcoming of this simulation, but it's a real effect, because when you're hard of hearing, then these hair cells that you've seen earlier are damaged, and this means that the information pathway from your inner ear to the brain is affected. So, and not as much information can be sent. Okay. We've been at the demo, and now I'm also facing this problem again. Okay, a bit better. The effects of hearing loss. So soft sounds are inaudible, and linear amplification is not really the best thing that you could do, because then you would also amplify loud sounds, and that would be too loud for the listener. We have reduced speech intelligibility and noise. Because of the reduced number of hair cells, people have difficulty of separating neighboring frequencies. So if you have noise, speech and noise, then a normal hearing person can separate them more easily than a hard of hearing person. This leads to the so-called cocktail party effect. So normal hearing people can usually discern or understand a person while other people are speaking simultaneously. And hard of hearing people have difficulties with this. And this leads to an avoidance of social interaction on the part of the hard of hearing. So they need hearing aids, but are hearing aids good enough? Not yet. But hearing aids, they make sound audible again. They have usually built-in noise reduction techniques that increase intelligibility and listening comfort. But listening with hearing aids is still difficult because hearing aids, well, they restore the audibility, but the reduced information channel that I told you earlier forces hard of hearing people with a hearing aid to spend mental effort into actually understanding what is being said. And this exhausts hard of hearing people, and they are usually happy when they can take out their hearing aids at the end of the day. And so we need better algorithms in hearing aids that can do this separation of voices in the environment. And that's yes, one thing that we do in hearing aid research. One thing that's also affected with hearing aids is stigmatization. Some people know that they're hard of hearing and know that they would benefit from a hearing aid, but they still don't want one because, well, a hearing aid, they say only old people wear hearing aids. And if I wear a hearing aid, it makes me, well, part of that group that is old. Well, it's not true that only old people wear hearing aids, but as I said earlier, hearing impairment is related to age. So what are the constraints on hearing aids? Well, the stigmatization leads to the point that hearing aids should be small, best would be invisible, so this is the cosmetic effect. We don't address this part in our research. Another thing is, for example, hearing aids should have multiple microphones because multi-microphone noise reduction techniques are the best to improve speech intelligibility. Calibration of hearing aids is tricky, and battery life is very important. Hearing aid manufacturers usually say our hearing aid lasts 1 week with a battery, and people don't want to deal with changing the battery more often. This might change because if you think of it, well, wearables are a hype. You can wear electronic devices on your body and they help you, and all people only think of smartwatches or such things. But hearing aids are actually wearables, so they help you, they do some computation, and they're always there and always on. They're actually medical devices right now. So it takes quite some effort to sell a hearing aid because you have to have it FDA certified and CE marked. So only a few global players actually sell hearing aids. This might change in future. So I've heard that the Food and Drug Administration in the US considers changing this, but this is not set in stone yet. But if it is, then openMHA, this platform, would be a good tool to hack your own hearing aids and publish. Okay, this is some slides about, well, hearing aid calibration is tricky. I don't think I will bore you with the details and give the stage to Frasher, who will introduce you to the openMHA platform. Okay. Oh, you want the mic.
Can you hear me? Okay, so yeah, my name is Frasher Loshaj, as Tobias mentioned, and I recently joined the Herzke R&D team, which should be in the logo in the header, which is invisible. And I will present I will give an overview of the software which was mentioned. Basically this platform which we provide, which is an open source platform. Mainly geared, it's a real-time audio signal processing platform, which is mainly geared towards hearing aid algorithm development. We had a pre-release in February with basic functionality, and we expect to have a full first release in June, which I should mention is compatible with, so it runs in Linux. So why this platform is good for? Well, I hope Tobias made a good case why research in the area of hearing aid is important. And but although a lot of research is done in this field, mostly is done by manufacturers, and the accessibility to these algorithms is limited. So providing open tools facilitates collaborative research. So what then we provide in order to facilitate this with this platform, we provide a complete set of reference hearing aid algorithms. We also provide a framework for easy implementation and evaluation of new algorithms. And since, as is, I hope, clear, this involves real-time signal processing, low delay is crucial. So this platform should really ensure that this is the case. And of course, we also provide a common library tool for signal processing as well. So the main component in order for this, so again, the idea is that this is an open source platform where researchers can collaborate and contribute. And so before going into details of the software itself and the sort of the usability philosophy that we envisage, I wanted to mention first the sort of main building block from the sort of developer side of where they can contribute, which is, well, similar to other platforms, I guess, a plugin, which usually implements a signal processing algorithm, which then can be included in some bigger chain of these modules to achieve a certain method of signal processing. What's important for both research and medical trials and so on is that users can change configuration settings at runtime, and in order not to disrupt the real-time signal processing, this problem is solved in a certain way in MHA, where the signal processing thread has a real-time priority, whereas the configuration change usually doesn't. So this doesn't. So the real-time processing is not disrupted. So for research, for developers to contribute, we provide plugins. We provide a template where these plugins can be implemented in C++. Again, before going to the software architecture itself, just to mention something a little bit of how what these algorithms are and how they can be implemented. As was mentioned before, in cases of hearing impaired persons, the non-ability to hear soft sounds is not the only issue, but also intelligibility in noise environments of the signal. So what's desirable is to have algorithms which can enhance signal-to-noise ratio. And for example, if one can use the adaptive differential microphone where one uses two microphones, and by assuming that the target is in the frontal hemisphere, for example, and the noise is in the rear hemisphere, one can have very good results in noise reduction. Another algorithm, so these are algorithms which are included in the pre-release that I mentioned. The other one is the coherence filter, which deals with feedback suppression between microphone and loudspeaker of the device. So one can use here, so it's a binaural algorithm. So by using coherence between left and right, by measuring coherence, binaural coherence, one can then have an adjustable, frequency adjustable control gain. Another crucial algorithm which is included is the so-called dynamic range compression. As was mentioned, for hearing impaired persons, applying just a linear gain, this of course doesn't work. So one needs to have an adjustable gain, a frequency-dependent gain control and gain rules, which in this case they address two issues. One is a way to create a gain rule for hearing impaired persons, but also it addresses the recruiting problem, which usually goes along with hearing impairment. More plugins will be available in June, so stay tuned. Okay, so finally we come to the structure of the software. So what we provide is a main host, the so-called MHA host in the diagram, which is a command line. So it's the main executable. It's a command line application which can be accessed. So it's a command line, but it also has a TCP/IP-based configuration interface. So one can access it with other control applications. For example, we show later a graphical user interface in MATLAB and Octave, which can achieve this. A crucial component, which was already mentioned, is plugins, and the host can serves as basically can load the plugins and also the input-output plugins, which facilitates interfaces with the audio backend. For example, one can have real-time input, like using jack or file or TCP/IP. And a crucial component is the toolbox, the openMHA toolbox, which contains, for example, what was mentioned before, the template for plugin development, but also other reusable data structures which are needed in signal processing applications. Some of the important features and services and conventions of the openMHA are listed here. For example, all these plugins, so basically a plugin receives a waveform, a signal in, and produces a signal out. In openMHA, both time domain and short time Fourier transform domain are supported. And what's important is that plugins can do signal processing in either domain. So you don't have to, every time a signal is sent to a plugin, doesn't have to do analysis and synthesis, which as we know will introduce extra delay. So this contributes in the direction of low delay that we want to have. An important thing is communication between, since we have this chain of algorithms used to achieve a certain method, we need to have some sort of a communication between them, and this is achieved by the so-called algorithm communication variables, commonly shared, like filter coefficients, for example, and so on. Also, we provide a plugin, a very important plugin which facilitates calibration between different. So in MHA, all plugins interpret. So the unit of the sound pressure wave is interpreted in the same way. So a floating point value is measured in unit Pascal. So, but since people use different devices, then one needs to have proper calibration. And the plugin, which is called transducers, is provided to help users with this. So this is the software itself, where we list, and there are many more features which are important. So if there are any questions, maybe we can answer them. So now I will try and say something about the usability idea. So who are the parties that would actually benefit from having a platform like this? So we think, for the moment, we think for this to be sort of structured in these three layers. So the first thing is audiologists and clinical, so the audiological and clinical context, for example, where one should be able to make out-of-the-box measurements and so on PC, so general purpose hardware, and change the parameters on an application level. The other layer is so-called application engineers. So I mentioned this so-called interface, which is a command line, so one can write, for example, input files, which are text-based. And the idea is that application engineers have enough knowledge of the underlying structure of MHA, so they can, by using the already existing algorithms, for example, the already existing plugins, they can come up with new algorithms, or in general, they can have a sort of a more advanced, they can access MHA in more advanced level. And the last layer is developers themselves. So people who develop plugins in C++, where openMHA is implemented. And yes, shortly we will see a GUI, but here just a teaser. So this is a GUI for the dynamic compressor, which is supported on Octave and MATLAB. So in this case, this provides a set of hearing aid fitting rules, and one can also save, for example, user data in database. And finally, so I mentioned the software. So if anyone is interested, and I hope you are, this is where you can find latest news and information, where you can also download the pre-release, which should be functional now. Also, there are guidelines on how to install it and also run some test cases that we provide. And I should just mention that this work is supported by National Institutes of Health. So thank you very much.
Microphones now. Hello, next is the demo. I hope you can see what I'm doing here. If not, please shout. So, seems to be... I've already started Jack. I'm now going to start the openMHA. This basically is just a small shell script that starts the openMHA, and also here in this case MATLAB for a fitting GUI. Because openMHA is just a command line application. It doesn't come with its own graphical user interface, but you configure it using a TCP connection. So you can implement your graphical user interfaces in any language that you want. Okay, it has a fitting interface. So this GUI has found the openMHA running. If I want to fit, I select here this test subject. The test subject has some audiogram. So, and first, you won't hear anything in this demo. I will, at some point, plug in these hearing aids into my ears and then show you spectrograms of input and output. But first, to explain this fitting graphical user interface to you. Sorry. You can see here that we can select between different fitting rules, and you can see here two displays for right and left. Because audiologists usually face their patients, their right ear is on the left of the audiologist, and that's why you usually have this in this way. You can't even see the left. I can shift it a little bit here. So, what you then see here, these thick lines, are the International Long-Term Average Speech Spectrum from a publication of at about 1999 or so. You can look it up. And we have just these spectra at different levels. And the audiologists now want to know what happens with my speech spectrum when I choose some prescription rule to fit a hearing aid. And I can then, usually you choose a hearing aid. Here we did choose the no-gain hearing aid, the no-gain fitting rule, because it's non-dangerous. And after that, after you fitted your hearing aid, you can fine-tune it with, say, 5 dB more at 2K, and then you can see here the output is different from the input. The input is here, this dashed line, and the output is the solid line here. And if I do this for a real fitting rule, I should first put the hearing aids in. So as you can see, these are no longer real standalone hearing aids, but we attached cables to it. Actually, the hearing aid manufacturer did this for us, because hearing aids are really small and require certain skills to attach cables to them. So if I now create this first fit for this real fitting rule, maybe you've heard initially some feedback. In this configuration, there's no feedback suppression. It's just a simple compressor. We also provide feedback suppression, but this very simple setup did not include it, but there are other samples that you can run. And I can now make it a little bit softer or louder again.
Can you show the gain? The gain adjustment is visible here.
Okay. I'm sorry. Yes, but actually I can't do anything. Just be informed. So here in the lower part of the screen that you can't see now, there are some buttons that say +5, -5, +1, -1 dB in certain frequency bands and also broadband. Okay. Now I close this, and you want to see the spectrograms. So I hope you can see this. This is Frasher. On the left channel here, I've put the microphone signal of my left hearing aid. So if yes. So if I touch my hearing aid here, I see broadband bursts in the spectrogram. And on the right part of the screen, you see the amplified sound. And you might be wondering why I'm wearing the hearing aids, which are now fitted for a hard of hearing person. And well, I think a researcher should do something like this, because you're basically safe if your hearing aid works as you intended to work. Because, as I said, the uncomfortable levels for hard of hearing people are often not elevated if you compare them to normal hearing people. So I am relatively protected from too loud sounds, even if I wear a hearing aid. Yes. But I must say it takes some getting used to actually listen to it, because, well, the high frequencies are amplified, and you can probably imagine how this sounds. Okay, that's it. I think we are finished, and we can take questions now.
Okay, thanks a lot.
Okay, now I've taken them out, and you probably hear this feedback.
So, do we have questions?
You partially answered this already, but I was wondering how you actually test those plugins during development. So you actually do hearing tests yourself. with the normal signal, and then it gets amplified, so that sounds totally different than what a hearing impaired will hear. Yes. So do you also have hearing impaired on your team who then test these things, or do you perform testing with patients? Or?
Yes, thank you for this question. Yes, I told you hearing aid algorithms need to be tested with real hearing impaired persons. And Herzke happens to have a sister company, the Hörzentrum in Oldenburg, and they have contacts, they have a database of 3,000 hard of hearing patients in our area, in Oldenburg and the environment of Oldenburg. And if you want to do some tests, we can collaborate with this Hörzentrum company and ask them to invite hard of hearing patients, and then we prepare a setup to actually test these algorithms in practice. But of course, before that, we also do the regular, well, when you develop software, you ensure that what comes out is really what you expect. And usually we don't, at Herzke, develop these algorithms ourselves, but we also collaborate closely with the University of Oldenburg, who have a large hearing research complex, and they develop new hearing aid algorithms, and we get them from them. Usually these algorithms are first implemented in MATLAB or some other high-level language, and then we translate them to C++ so that they can run in real time. And then, of course, we have a source, a MATLAB source that we can test against. Do we still produce the same signal? Usually we have to optimize somewhat when we translate to C++ so that it also runs in real time. And then we have to wager whether the differences that we introduced are still okay, and this is still basically the same algorithm. So there are software quality techniques that we employ, and of course the validation is then, does it help the patient?
Okay, I have myself a question. So in the examples that we hear, how do we were supposed to hear what someone with hearing impairment was hearing?
Yes, it's an oralization of hearing impairment. When you say, or when you ask, is this the exact same perception that a hard of hearing person has that I have now as a normal hearing aid person, then this can degrade into a philosophical question. Like, if I see a blue wall and you see a blue wall, do we have the same perception? Or, well, but we can say that we simulate the effects that we know of, the damages that are there in the auditory pathway. And therefore, we are relatively sure that this is a serious oralization of hearing impairment.
Okay, thank you. Another last short question? No.
Just to have an idea, what is the processing power which you do have available for hearing aids? In floating point operations per second, something.
You mean for real hearing aids,
yes.
The final product? Yeah. I'm not a hearing aid manufacturer. I cannot really tell. In the end, when we have an algorithm and say it works, then it's the job of a hearing aid manufacturer to actually implement it in hardware. Of course, nowadays, there are also a different option, like implement these things on a smartphone or things like this. And yes, you can just always take all the processor power that you have there. Usually, the more processor power, the better. But of course, you have to somehow cope with the realities and, well, dump down or to optimize your algorithms and change them a bit, and then test if you still achieve your goals.
Because some of these frequency domain things are not so simple, in fact.
I didn't get
some
that.
of these frequency domain algorithms, they are quite CPU hungry.
Yes, they are.
Okay, thanks.
Okay, thanks again.
Thank you.